Hey everybody, I'm back here in the shop and I'm still working on the Cincinnati #2. What you see here is our display. This is the DR.DRO. You will find the project on Github. You have seen it in some other channel videos as well. Today I want to go a little bit more in detail about this because I think we have an interesting application for surface grinders and for tool cutter and grinders. I will show you how I connected this display to the machine, and I will show you how I'm using the display to control our work head. Let's go through the basics. I will show you all the connections. We will also go through the settings on the display. We will see how to configure the scales. We will see how to configure the motor, and we will see how to do some simple indexing and some access follower applications. So we are at the back of the display right now. This is the 3D printed enclosure. Models are available on GitHub if you want to print it yourself. This model uses the Raspberry Pi display, so if you want a bigger or smaller display, you will have to make your own box and your own enclosure, but you can of course use whatever display you want. The back of the normal display will come with a PG connection here, a PG gland that you can use to connect any cable you want. And then it comes with this power supply. I'm not using this one because for this quick test I'm using the same power that is provided to the servo motor to also power the display. It is not an ideal setup, but I don't have enough cables right now to get it all connected the way it should be. So I'm sharing the power supply. This is where the power comes in. I will show you the connections that I have made. And this is also where the control signals come from the DR.DRO and go over to the servo control box. This is one of the many stepper online or similar controllers that allow you to use a stepper motor with digital signals. We'll go over this in a second. You got 4 connections in here. These 4 connections are for 4 linear scales. You don't have to use all of them. As a matter of fact, I'm using only one right now. You can use any of them. And we'll see also about the connection of this. But it's all pretty straightforward. The pinout is one of the many standards that I found online, so most likely you will buy scales that are not compatible, but there are very easy to rewire connectors available on the market. I have them on sale on my webpage as well that have screws here, so you can pretty much rewire any kind of linear scale or encoder the way you need it to work for this display or for any other for that matter. So again, this is where the linear scale comes through, and this is where power comes in and control signals go out. So I will show you the other end in a second. This is kind of a difficult shot, but I'm going to try to give you a quick description here. I'm using a Cat5 cable, and I'm using pairs to send the signals over to the stepper motor controller. And then I'm using a couple of spare wires, the only 2 spare actually that I have available, to provide the power. The display itself does not use a lot of power. It needs about maybe an amp when it's fully loaded at 12 volts. And right now I'm using like an old laptop power supply which provides 19 volts. It's a decent compromise for powering this stepper online controller as well as the display. Just to remind you, the power supply that goes over to the display needs to be within 10 volts and 40. Ideally 36 I would consider to be the maximum, just to stay on the safe side. So anywhere nearby that will work. 19 is pretty much in the middle, so it's going to work just fine. Now what you see here is all the twisted pairs that I am sending over, and the signals that our display sends out are the pulse signal, the direction signal, and the enable signal. The enable is normally kept active pretty much all the time whenever you have this axis selected. You need to have this enable signal active, otherwise this drive will be disabled and the motor can be spun freely like you see right now. This is just the normal resistance you get from a stepper motor. When this enable signal is active, this one has got more holding torque, which is the nominal torque of the motor and the controller itself. And then you got all a bunch of settings in here that we're going to be looking at when we set up our parameters on the display. Right now I have set this to a very low value, which is 400 steps per revolution. It's working good enough for the test that we are going to perform here. We can always increase it, but remember that the best accuracy is the one you get from the motor itself. And this motor, I think it's 400 steps per revolution, so we are doing 1 step per pulse. Maybe it's 200. I'm not sure right now. I don't remember exactly. But if you go in you know, subdivisions of these steps, it's not going to be a precise position on the magnetic pull of the motor. So you can send it out. It will make the drive smoother, but I would not rely too much on the accuracy that you get out of the motor when you're going with a finer step subdivision on the control box. So 400 seems to be a decent compromise. The other issue you might have if you go with very fine counts per revolution is that our controller can only generate up to 50 kilohertz signals going out to the motors. You might be limiting the maximum speed of the motor. So if you're trying to address some fast spinning operations, or if you want to have more performance out of the motor, then you want to stay on the lower side. So both these reasons kind of you know, suggest you should stay on a fairly low value for these guys. When it comes to the current, I'm actually giving the maximum to the motor. I think it's probably killing our power supply a little bit, but again, this is a low torque application, low speed application. There is nothing specific or special going on in this simple demo, and we're just gonna see how this works. So now you have seen the connections here. I mean, they're fairly straightforward. I'm giving 1 ground for each one of the negatives. I'm giving the output voltage to each one of the positives, so they are pretty much balanced. I'm just trying to keep the signals, you know, integrity a little bit better. So I'm using all the cables available in here, and you've seen how this goes connected over to the display. This is on the back. We can open this up. Maybe we will do it in the lab so you can see. But the labels and the names of the signals are exactly the same as what you would find on the stepper motor driver right here. So it's just a matter of wiring 1 to 1 and then sharing 1 common for what is going to be your +5 volts coming out. Speaking of which, side note, some controllers have this. There is a small switch here on the side. This small switch is used to select whether you want to have 24 volt control signals or 5 volt control signals. We are using 5 volts control signals right now, and that's why I have this one positioned on the 5 volts position. And that's pretty much it. So next we're going to take a look at the boot up sequence on the display. And we're going to take a look at how to configure our scale and how to configure our stepper motor access control. All right, so I have flipped the display around. We're in the same position where we were before. Here's our motor, here's our display. I'm going to now flip the switch, and we'll see the boot sequence taking place on our display. Should take less than a minute to boot up. If it's your first boot after you got the display unit or after you flash the memory, the first boot will take a little bit longer because it's doing a resizing of the SD card to maximize the available space on your device based on the memory card you have. So, and it will also set up SSH keys and do a couple of other operations. But just wait, be patient. The display will come up. Once you reach this screen, then it means that you are on your device in your home page. And that's what you see here. So as you can see, my scale is connected on the second axis, which right now is marked with a question mark. And we haven't checked on any other settings, so we're going to do that right now. And our motor is not enabled. Everything is gray here, so we're good. And the communication is currently working fine. You can see the green COM over there on the top left corner, so that means that the display is communicating. We'll go over what this display does in a second, but I just want to start from our base configuration settings so we can get our linear scale and our rotary head properly configured with the parameters we have. So I'm going to go over to the gear button. On the gear button you get all the settings. There is a selection menu on the left. You got all your scales. So we care about scale number 1. We're going to touch that one. First thing I'm going to do is I'm going to change the name. I'm going to call this one, this is going to be my x-axis, so I'm going to select X in here. The other scales, they are not used right now, so I'm going to go over them and I'm going to just cancel or leave this empty just to declutter the home page. I will eventually add a feature that allows us to select and combine axes, but right now it's not available on this display, so we're just going to have to deal with this. Now, let me bring you over at the linear scale so I can show you which model I'm using. This is a very, again, quick and dirty installation. We got some specs in here. I don't know how easily you can read them. I don't even know if they are on focus, but I'll stay a little bit farther, so probably you can read something. So this is a linear scale. It's one of the many Chinese linear scales you can buy. They're very cheap. They work very well. It's a glass scale, and this one has got 5 microns resolution per step. So this is the number that we care about. And then we got total length of 300 millimeters. I used my spacer here. This came with the scale, just to quickly align. You know, made some clamps. Maybe I'll release a video about those. Got plenty of footage, but it's not really interesting. Just, you know, a few brackets. Made it in a way that I didn't have to modify my surface grinder or drill holes, my tool cutter and grinder, and just got it fairly lined up, and you know, it's already working and it's looking pretty good. So again, 5 microns per step, and then we got our length of 300 millimeters. We don't really care about the length. What we care is this number here. The 5 micron per step is what we want to know, so we can set it up accordingly in our display. So let me go over back at the display, which is right here, and here you can see we got a ratio numerator and a ratio denominator. So these two numbers are what allow us to define what's the conversion factor that we want to apply between the encoder counts and the display counts in millimeters. So if every step is 5 microns, it means that whatever number we take in counts coming from the scale needs to be multiplied by 5. So our numerator will be 5, and that's what you see here. So if you need to change it, you can go in here and you can say 5. And then the denominator, I don't know if there is ever going to be a need for that, but that allows you to pretty much define a rational ratio between whatever the count is and the displayed value on your screen. So normally stays at 1, but I don't know, there might be situations in which this number needs to be adjusted. Let's say you have a 1 micron scale, then you would go here and type 1. If you have a 10 micron scale, then you would have to type 10 in here. Right now, the accuracy or resolution of the display is based off of 1 micron. So if you have a higher accuracy scale, then you're going to have a problem because the display will not be able to support it. Let's go now and look at the servo configuration. There's a few more things in here, and some you will have to figure out yourself, but let's go back to our setup here. This guy here, if you look at the motor, this has got a 15-tooth pinion, and this gear has got 90 tooth. So 90 divided by 15 gives us a ratio of 1 to 6. We need to remember that, 1 to 6. And then every revolution of the motor right now is configured to have 400 steps, okay? So what we need to figure out is how many steps it will take to make a full revolution of this circle here, to make 360 degrees on this output shaft. So if we do the math, we're going to have 400 times 6 is going to be giving us the full revolution here. 400 times 6 is 2400, and that's exactly the value I have set right now on our display. Oh, let's just pretend we still have to set this, so I'm going to set this one to 2400. Now there are three more important values in here. We got the speeds and we got the acceleration. Now these depend heavily on what type of servo and what type of power supply you have available to you. So right now, minimum speed can always be set to 0, unless you have some special requirements due to your servo, but I'm going to set it to 0. And then the maximum speed, you have 2 columns here, see? The column on the left is in steps per second. So you probably know by looking at the data sheets of your driver and motor what the maximum speed can be. And that gets translated in revolutions per minute this is actually, I think it's in degrees. Yeah, this is in degrees per second, okay? So this is going to be in degrees per second. So 6,000 steps, they translate to 900 degrees per second, okay? So I normally look at the ones on the left because I know the specs of the motor. You might change the ratio, and if you change the ratio, the value on the right will be adjusted. But what you care about is the one on the left. The one on the left is the one that is dependent on the type of motor and drive you have. So these values that I'm using here are kind of, you know, working well for the setup I have. They're kind of already stretching a little bit, so I'm going to lower them a little bit. Let's put it at 4,500, for example. And then the acceleration can probably be kept, yeah, fairly high. I think it's going to be fine. Let's leave it at 16,000. That's going to be fine. Okay? So that's all there is to it. Okay, so let's look at the setup here. I'm going to use this indicator not as an indicator, of course, just as a pointer, and make it so that we can repeatedly go there. Okay, so we got our mark here. Again, this mark is just for us to verify, where we are with our initial mark. This is our index. Well, right now we are on the index 1, so just remind that I'll show you on the display. Right, that's where we are. I went ahead and I selected the axis by pressing on the R. It turns on green, okay? So anytime you want to make anything with your indexing mode, the axis needs to be enabled. And as soon as you press the button, the enable signal goes out. So again, axis is selected. This is our current position. We are at 180 degrees. We set our system to actually perform 2 divisions. Imagine a 2 flute endmill, for example. And we are at index 1, which is between 0 and 1. So this is already our second step. So here's where we are. And you can see where the line is, right? I hope you can see. I don't know how well that is visible, but there you go. That's your mark, okay? So now what I'm going to do is I'm going to press the button. We are now on the opposite to the line that we just made. Let's go forward one more step and we should return to our initial step. And there we go, okay? So let's now set 3 divisions, for example. Actually, you know what? Let me do this. It's going to do offset 180 and 3 divisions, and we go to 0. There we go. So this is still our 0. I set now the DR.DRO to work with 3 divisions right there, and we will take a look at the full rotation here. So I don't know if you can see both in the same shot. Let me try to do that. It's pretty bad. Maybe if I move this table a little bit. As you can see, the linear scale is also working. We'll take a closer look at that in a second. But yeah, I think you can see both in the same shot. So here's where we are, okay? This is 3 divisions. We are at index 0. Index 0 right now is marked. That's where the marker is. We're going to go 1 step forward, 2 steps forward, 3 steps forward, and we should have the same distance from the mark that we prepared before. We can do this several times. All the positionings are relative. The DR.DRO does not have an absolute position, so it's always calculating the distance to your next step. So you can rotate indefinitely. This is important if you want to, for example, do continuous rotation operations such as threading or hobbing with the milling machine, or threading with the lathe, for example. So that's why everything is relative. So which is, things we're going to be covering in the next videos. But let's verify and make sure that our blue mark does not move as we keep going forwards a few times. That's still the same. Still the same. Still the same. So I think we got a good setup right here, okay? This is kind of telling me that our ratio is set up correctly. Now, of course, if your ratio calculations are wrong and you have a wrong value configured in your settings page, then this is not going to happen. You're not going to be able to return to 0 when you rotate in your axis. So that's why I'm making this check. Now let's go back to the other thing we configured, which is our linear scale, right? So let me see if I can set up something with our dial test indicator here, so we can also verify that the display is indeed sending or telling us the correct distance when we move our x-axis. Let's just turn around the display. So here's the real cool feature of this display. The synchronous motion capabilities are what really differentiate our guy here from anything else on the market. This is what allows our display to become an ELS. It is what allows our display to become a single axis servo controller. It allows us to do helical grinding or machining. It allows us to do hobbing and who knows how many other things. Those are the first that came to mind, but you can probably do tapers on the lathe with this display. You can machine tapered screws. You could machine helical gears, as I said before. You could machine worm gears, and you can replace your Norton box with this and use it as an ELS without any problems. I will now show you what happens when we enable the servo mode. So I'm gonna do, well, let's go first go over to the settings, right? So what we have here is we have our current axis coordinates, which is right here. We can change that. We can set the value however we want. We're running in millimeters right now. And then we got these two boxes that we skipped over before when we were looking at the settings. We got a numerator and a denominator. Now the way these two numbers work is fairly simple, but you need to know how they work, of course. Your output axis, you can see it as the output axis, and denominator is your input axis. What do I mean by that? Well, if you read this, this is telling you that if I enable this synchromotion, we're going to be performing 360 units at the output, so 360 degrees for 100 steps or units at the input, which right now is millimeters, right? So what this ratio here sets, it says that over 100 millimeters, we're going to do a complete rotation of our output axis. And if you want to change that, it's easy as just clicking in here and saying, you know what, I want to do a full rotation in 50 millimeters. Show me how you do that. So you put 15 there, you select your axis by pressing on the green. Right now, you're not going to be able to change it. This is to prevent you from having your tool or your workpiece jumping around and damaging your work. So we disable it when the servo motion is enabled. And now that we have this enabled, well, let's see what happens. You can tell already what happens. Do I have the braking gauge? Oh, I'm sorry. I need to undo this guy here. There we go. But you already could see that our work head was rotating, right? So if I move it now, you can see how the motor spins, and it spins in accordance with the position of our x-axis. Now what's cool about this display, I don't even know if that has got any applications in the real world, but I thought, you know, why not? Let's do it. One cool thing you can do here is you can enable more than one axis and follow or track the position in the same synchro approach with multiple axes selected in your display. So you can do compound interpolation of the position of more than one axis. I still have to think about it. I don't know if it's useful for anything, but it can be done. So if you know how we can use that to do something fancy, well, let me know, because I'm curious to try. So, well, you're seeing here, right? And this is our work head spins, and this is our display. It's all showing in real time here, or nearly close to real time, close enough, I would say. Now you see there is a bar on top, this blue bar that moves. That bar is going to tell you how fast you're going compared to the maximum speed that you configured in your display, right? So let's go back there. So you can see here that is on the servo, we got our maximum speed, which is now set for 4,500. Well, that maximum speed will define the maximum of this progress bar here. That is very helpful because as you are doing your machining operation, you want to know if you are getting too close to the limits of your motor. So as long as this bar is not 100%, it means that the motor will keep up and the display will keep up and the motion will be tracked perfectly. If you are passing that, then you got a problem. If you're going faster than that, then you got a problem. Now, all these things that you have seen, so we're in synchro motion right now, right? You can see that, you know, the motor is moving synchronously with the position of our table. I can still do my offsets, so I'm going to set this to 0 now, and you see that we quickly position and everything stays, it's 180 degrees with reference to our position on the x-axis, okay? No, nothing is lost. Same applies to divisions, right? So if I go to my next index, I am still tracking my position, I'm still in synchro motion with my x-axis, everything is still perfectly tracked. I can also do my divisions. This is very important because think about grinding flutes on an end mill, right? You're going to have 2, 3, 4, 5, 6 flutes, however many you want. And you're going to have to do indexing, but you also are going to have to do your synchro motion. So the two things need to work together. And that's what we got here, okay? Now, I'm going to go over this way more in detail, but I don't want to bore you to death with this right now. I think this is pretty cool. And I think what I want to do next is I want to try to grind, or let's say regrind or resharpen, that's an easier operation, as a first step. Let's try to resharpen the flutes on an end mill, because I want to see how that works. Now, if you need to change this number, we're going to see how to set it up for an end mill based on the flutes that you have, but you just disable this. When it's disabled, you can move, and at this point you have lost your synchro positioning, okay? So it's important to remember that when you enable this axis again, it's going to restart moving from that specific point. So make sure that you stop on a known position or that you verify that your alignment is correct before you re-enable it. That is very important, for example, if you want to change the ratio, right? So maybe go back to 0, you know, make sure that your output axis is on the same coordinates so that when you re-enable it, you don't have a disaster in your hands. Let's try to set this one to 200, for example, just to see and show you how the ratio can be changed dynamically and how everything works. So I'm going to select the axis again, and as you can see now, you know, the rotation ratio is more like what an end mill probably will look like. It depends on the helix angle, but yeah, that's pretty much it. So let me get everything set up for regrinding the flutes on an end mill. I'm sure it's going to be a disaster because it's the first time I do it, but let's see how we go about this disaster together.